When it comes to causes of climate change, we tend to think of cars, the fossil fuels they use, the greenhouse gases they emit, industrial waste and emissions, deforestation, etc. However, we rarely think about food. When actually, food waste accounts for about a third of all municipal garbage. It then needs to be incinerated, which increases air pollution, discharges ash and flue gas into the atmosphere. In fact, food waste contributes to approximately 29% of the country's creation of greenhouse gas emissions. So, how can this problem be solved? Simple. We can turn it into bioethanol. Bioethanol is an alternative fuel frequently used as motor fuel or as an additive in gasoline. It also serves as an option for a cleaner, more renewable, and greener form of energy. The production begins with selection of food waste, which generally contains carbohydrates, starch, proteins, lipids, cellulose, and hemicellulose. But only the food waste rich in carbohydrates and starch are selected for use as a raw material in bioethanol production, as they are the ones found in abundance in most food waste. Next, a pretreatment step is needed to alter the food waste structure to allow more access to it in terms of the surface area for the fermentation enzyme. Although many different types of pretreatment techniques exist, such as ultrasound, fungal mash, acid, and alkali, the conventional method, acid pretreatment, is still indeed the preferred pretreatment method for use at the plant scale, owing to its low cost, high yield, and time efficiency. For instance, an addition of commercially available sulfuric acid will hydrolyze the biopolymer cellulose and generate 31.03 gram glucose per liter hour. The third step is saccharification and fermentation, where the sample's digestibility is increased and the food items are turned into bioethanol by fermentation microorganisms. For this step, although there are many techniques available, including separate hydrolysis and fermentation, simultaneous saccharification and fermentation, as well as non-isothermal simultaneous saccharification and fermentation, the third one is preferred in terms of the volumetric productivity, time required, and ethanol yield. For instance, a study conducted using this method acquired a maximum ethanol concentration of 53.90 gram per liter after only 38 hours of fermentation, with the yield of 0.15 gram per gram and a maximum theoretical percentage of 73.26%. Post-fermentation, the bioethanol mixture is further processed in order to recover the desired ethanol. Distillation, which is the conventional method employed for this step, is relatively energy intensive and accounts for a significant proportion of the bioethanol production cost. Therefore, we propose different energy-saving alternatives, which include heat-integrated, membrane-based, feed splitting, and ohmic-assisted methods of distillation. From this, it was found that feed splitting, which involves the use of a heat exchanger to heat the feed flow by cooling the bottom product flow, is preferred because of the high ethanol yield, which was 99.2%, and also because it reduced energy usage by 27%. The bioethanol mixture also contains residues which possess potential biological activity but are often discarded as contaminants. Owing to this, several techniques such as the use of pulsed electric fields, ultrasound, microwaves, supercritical fluid, and enzymes are proposed in order to look for a greener bioethanol recovery method which also allows the isolation of these residues, where it was found that the enzyme-assisted extraction serves as the best technique as it led to the highest product yield of 94.9% in a past experiment performed, which is much higher than that of the other methods employed. In this way, food waste can be made of some use and turned into something beneficial, such as bioethanol, along with other compounds possessing biological activity and use. Thank you.